Quindi direi che possiamo iniziare. Okay, so last time we introduced to the theory of Dirac, that is the theory of quantum relativistic equation for, let's say, fermions, so spin one-half particles, as we will see today better. So essentially, this equation was introduced by Dirac in 1928. Trying to solve the problem of making quantum mechanics Lorentz invariant. The first attempt, if you remember, was already provided by Klein and Gordon, who provided, in fact, a Lorentz invariant equation with second-order derivatives both in space and in time that is suitable for scalar bosons, so a particle with spin equals 0. Okay. Nonetheless, that equation introduces also some problems, such as negative energy solutions, a completely wrong value of defined structure constant, the alpha of electromagnetism, and also a non-positively defined probability density. Then Dirac started from a new concept. Okay, instead of using second-order derivatives, he wrote his Hamiltonian in terms of first-order derivatives, both in time and space. And he introduced the formalism in terms of the alpha and beta matrices, and later on also in terms of the gamma matrices, the so-called Dirac matrices. And at the end, he obtained this, the equation that you see here, which is now written in the, let's say, explicitly covariant form, and which, in fact, this is nothing else than the equation of motion for quantum relativistic fermions, such as electrons, for instance. Now, we have also, we derived also the adjoint Dirac equation after defining the adjoint spinor, where spinor is, in fact, the solution of the Dirac equation, which is a four-component, essentially a four-component wave function. Then we went through the solution of this equation, okay? So what we did here was, let me go here now. Okay, so one first type of solution was derived by assuming for a free fermion of mass m that the solution has to be of the form of a plane wave in this way, where U, EP is a four-component spinor. And then we found that by solving the system, homogeneous system of two paired equations, that we get here four different solutions. Okay, the first two corresponds to positive energy, and the second two corresponds to negative energy. Okay, that was originally a problem to understand and to interpret correctly. But then we also saw that we can also solve the same Dirac equation if we swap the sign of the energy and momentum simultaneously. So we look for the solution of this type here, where now the four-component spinor we call V, to distinguish with you. And then we have this extra minus sign here that accounts for this double sign change here. And we get another set of four independent solutions. We call V1, V2, V3, V4. Again, the first two corresponds to positive energy and the second two to negative energy. So in total, we have in end 8 different solutions of the Dirac equation. Although, of course, only 4 are independent, so we have to make a choice here, okay? And based on the, sorry, let me do this a little bit more. Ok, perché si vede così? Ammetti. Allora, perché se ne è scelta giù? Ah, ok. So based now on the Feynman-Stackelberg interpretation, okay, the negative energy solutions, so U34 and D34 corresponds to unphysical negative energy particle or antiparticle which propagate backwards in time. Okay, so these essentially are meaningless. And so the four solutions that we will be using from now on are only the positive energy solution, okay, which are interpreted in the Feynman-Stackelberg interpretation as physical particles and physical antiparticles, both moving forward in time with positive energy. Okay, so this was our arrival point at the last lesson. And also let me now again write you the full expression of these four solutions that we derived. So we derived essentially the first two, but then in a similar way one can derive the other two. So these are the two particle solutions, U1 and U2, and these are the two antiparticle solutions, V1 and V2. okay, which are expressed in terms of the energy and momentum of the particle. Now, having understood the distinction between particles and antiparticles, okay, solutions, we still have to understand why there are two solutions for each category. So why do we have two particle solutions? Why do we have two antiparticle solutions? What is the reason of this twofold degeneracy? Okay, so this we have understand today. Now, as you know, in physics, an energy degeneracy implies the existence of a conserved quantity. Right? This is general. That means that, in other words, there must be a physical observable that commutes with the Dirac-Hamiltonian. Those eigenvalues can be used to possibly distinguish between the two degenerate states. So we need to find, let's say, a two-valued observable which commutes with the Dirac-Hamiltonian, and this can be used as the tool to distinguish between the twofold energy degenerate states for both particle and antiparticles. So, of course, it might be tempting to associate these twofold degeneracy to the two projection of the spin of the particle and antiparticle, so spin up and spin down. This will be, of course, the easiest thing to think about. So let's see now how the spin operator is introduced in the Dirac theory. Okay, so in Dirac theory, we have not a standard wave function, but four component spinors. So the spin operator has to be in the form of a 4x4 matrix, which is defined this way. So this is the spin operator, is written in terms of 1/2 of this sigma matrix, which in turn is given in terms of the Pauli matrices. So there are three of these. Each time we have sigma 1, sigma 1, sigma 2, sigma 2, sigma 3, sigma 3. Each of those is the standard 2x2 Pauli matrices. And of course, as you know already from non-relativistic quantum mechanics, the spin operator must satisfy this commutation relation between the three components. Now, very interestingly, in fact, it turns out that the Dirac spinor, so any solution of the Dirac equation, are also eigenfunction of the squared spin operator, S squared, with spin 1/2. So essentially, any spinor, so any solution of the Dirac equation satisfy this eigenvalue equation for the squared spin operator, where S is exactly equal to 1/2. So let me now show this. So I'll now move to the blackboard. Ok, io adesso mi vedo a schermo pieno. Spero di stare registrando correttamente. Ok, give me one moment. Ok. So I will show you now that, in fact, any Dirac spinor is an eigenfunction of the squared spin operator, corresponding exactly to spin 1/2. Okay, so our squared spin operator is 2. Okay, stay here. S squared. We add this on our four component. Ah, siamo fuori dal campo. Okay. Ah, perché si è girato? Ah, perché si è girato il computer. Ecco qua. Vediamo un po' se riesco a inquadrarlo meglio. Più lontano. Che si muove al contrario di come vorrei farlo muovere lei. Ok, così dovrebbe essere meglio. So, questo lo vedete?
Sì, sì.
Okay, so we are now applying the squared spin operator on our spinor. The squared spin operator, as defined on the slide, is just 1/4 of this sigma squared operator acting on the side. So this we can also make explicit, so 1/4, and then we have the three components, so sigma 1 squared plus sigma 2 squared plus sigma 3 squared acting on our spinor. where again sigma 1, sigma 2, sigma 3 are 4x4 matrices expressed in terms of the Pauli matrices. So to make this more explicit, this is going to be 1, 4, and then we have this square operator is nothing less than sigma 1, 0, 0, sigma 1 twice. Then we have plus sigma 2, 0, 0, sigma 2 twice. Then we have sigma 3, 0, 0, sigma 3 twice. All these acting on our spinner. So let's make this even more explicit. So this will be 1/4. Now we substitute here the Pauli matrices. So the first one is going to be 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. And the second is the same. I will not write this, but it's the same. Plus, now we have 0 minus I, 0, 0, I, 0, 0, 0, 0, 0, 0, minus I, 0, 0, I, 0. And then it's the same. And then we have the last one, which is 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, minus 1 times the same, and all these acting on side. Okay, so each of these minor is a Pauli matrix according to the formula above. Okay, now we can make the product of these two matrices, that is squaring the Pauli matrices. And it turns out that each of these square matrices is just the 4x4 identity matrix. So this is going to be 1, 4. Okay, then we have the I plus I on the side, where by I mean the identity matrix 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So this is 1, 4 times 3 times the identity matrix, that we can forget for the moment because the identity matrix of the spinor gives you the spinor. So this is 3, 4 of the spinor that you can write more explicitly as 1/2 plus 1 in the spinor, which is nothing else than the S, well, the square spin eigenvalue, S plus 1 psi, when S is exactly equal to 1/2. Okay, so overall, we obtain now the eigenvalue equation that you see already in the previous slide. So S squared psi is equal to 1/2 plus 1 psi, which corresponds to S plus 1 psi with S equal 1/2. Okay, chiaro?
Okay.
So the good news is that spin 1/2 comes automatically, okay, naturally from the Dirac theory. We don't have to put it by hand as we did in the non-relativistic quantum mechanics. Okay? And this is the proof that, in fact, the Dirac equation describes the motion of the dynamics of free spin 1/2 fermions, such as the electron, for instance. Okay? Now, let's come back to the slide. Ok, vedete la slide adesso?
Sì, sì.
Sì, sì.
Ok. No. Okay, so as I was saying before, the Dirac equation provides a natural description of spin 1/2 particles. So the spin emerges naturally from the theory and doesn't need to be introduced ad hoc as in non-relativistic quantum mechanics. Now, a very nice consequence of this is that the Dirac equation allows to compute correctly the energy splitting of atomic levels due to spin orbit and spin-spin interactions in atoms, which corresponds, as you know, to the fine structure and the hyperfine structure of the atomic energy levels. And this in fact, yields the correct value of the fine structure constant, alpha, 1/137, okay? And this was, if you remember, one of the three main products of the Klein-Gordon equation, okay? So the Dirac equation also solves this problem, okay? So it corresponds to the correct experimental value of the fine structure constant. That's, of course, a very nice feature. Now, we have spoken about spin. There is an important observable that we will also study a lot during our course, which is related to spin, and this is the magnetic moment. So this is a very general formula. So in general, for a particle of charge Q, mass m, and spin s, the magnetic moment is a vector which is defined this way. So Q is the charge, m is the mass, s is the spin, and g is a constant which is called the gyromagnetic ratio. Now, there is a precise prediction by the Dirac equation, by the Dirac theory, that the value of G must be exactly equal to 2 for any Dirac particle, where Dirac particle in general means a point-like particle with spin 1/2 satisfying the Dirac equation. So, for instance, the electron or a quark and so on. Okay? So for a point-like spin 1/2 particle, the Dirac theory predicts exactly that G, for this gyromagnetic factor, must be equal to 2. So then for a Dirac particle, you can just simplify G with the 2 in the denominator, and the magnetic moment for any Dirac particle is predicted to be given simply by Q over M and the spin. Okay? Let me just anticipate now something that we will study later. You know that, for instance, the proton is also a spin 1/2 particle. It is a fermion. Okay. However, it is not a Dirac particle because it is not point-like. The proton, as you know, is a composite object. It is made by quarks and gluons, so it is not a solution of the Dirac equation. And in fact, for the proton, G is very different than 2. Okay, as we will see. Okay, now. So we have still to solve the problem of the two-fold degeneracy, okay? So in order to prove that the two-fold degeneracy of the solution of the Dirac equation corresponds to the two opposite spin projections, so spin up or spin down, one has to demonstrate that the Dirac spinors are also eigenstates of the spin operator. So not only of the square spin operator, but also of the spin operator. Or in other words, one has to show that the spin operator commutes with the Dirac Hamiltonian. If you are able to prove this, then you are done, because then the spin is something that is a conserved quantity. It commutes with the Dirac Hamiltonian. It has a two-fold values, up and down, or 1/2 and -1/2. So it can be indeed used to interpret your result, okay, your two-fold degeneracy. However, it turns out that this is not the case. If you calculate the commutator of the spin operator with the Dirac Hamiltonian, that you write here written explicitly, okay, and also the spin in terms of the sigma operator, then you see that the commutator is not 0, it's something different than 0, it's given by this vector product here. And therefore, the spin does not correspond to a conserved quantity in the Dirac theory, and thus it cannot explain the two-fold degeneracy of the Dirac solution. Okay, so we had a good idea, but the idea is wrong at the end. What about the orbital angular momentum? So the orbital angular momentum L also does not commute with the Dirac Hamiltonian. If you calculate again, okay, I don't care about the algebra to show this, so you can find in the probably textbooks. But the important point is that also L, so the orbital angular momentum, does not commute with the Dirac Hamiltonian. So again, you see something different than 0 here. So also the orbital angular momentum does not correspond to a conserved quantity. However, this holds for the total angular momentum J. J is defined as L plus S, so orbital angular momentum and spin. If you now calculate the commutator with the total angular momentum with the Dirac Hamiltonian, then you find that it does commute. Okay. So the total angular momentum is indeed a conserved quantity and constitutes a good quantum number. However, it is not a two-valued value. Okay, a two-valued operator. You can take essentially any value. So we cannot use this as an argument for the twofold degeneracy anyway. Okay. Let me now make some comment here. So with the simultaneous replacement of E to minus C and P to minus P that we applied to derive the antiparticle spinors, if you remember, also the orbital angular momentum changed sign. Okay, so for the positive energy solution, it is defined in the usual way. Let's use the classical definition here, so R vector P. But for the antiparticle solution, which comes with this opposite sign energy, okay, any momentum, you get a minus sign here. Okay, so the position vector stays the same, but the momentum vector changes sign. And so overall, for the antiparticle, your momentum changes sign. Since we want still to fulfill this commutation rule here, okay, this can only be possible if also the spin operator changes sign for antiparticle solutions, so that the spin operator for the antiparticle is minus of the spin operator for the particle that we so far just called like S, simply S. Okay, so if you allow both to change sign, then this is fulfilled as you want to be. Okay, but we are still at the beginning, okay, of our problem. We still need to justify the twofold degeneracy of the solution Dirac equation. And as we have shown, this cannot derive from the two-spin projection because the spin operator does not commute with the Dirac Hamiltonian. Therefore, we need to find another two-valid observable whose operator commutes with HD, okay? And this observable turns out to be helicity. So what is helicity? This already you know, of course, from the previous year. Helicity in general, and also classically, of a particle with momentum P and spin S is defined as the projection of the spin in the direction of motion. Okay, so you have the scalar product here divided by the modulus of P. Okay, so essentially H can also take either 1/2 or the same value of the spin. Okay, so if this is the momentum vector and this is the spin vector, the helicity is just the projection of the spin vector in the direction of the momentum vector. Okay, and it is defined in this simple way. Now this is the standard definition. Of course, now we have to translate these into the language of relativistic quantum mechanics. And so in relativistic quantum mechanics, the helicity operator is given in this way, where now these are operators. And so for the spin operator, we use 1/2 sigma that we defined before, and then we have the momentum operator. And so now we can put everything together here. We have a scalar product, so we can put everything together in this matrix form. Okay, so this is the helicity operator, which again is a 4×4 matrix, since those sigma here are again the 2×2 Pauli matrices. And indeed, it turns out that the helicity operator commutes with the Dirac Hamiltonian, okay? Although only for the case of massless particles and massless antiparticles, okay? So for the moment, let's forget about the mass. Suppose that all particles and antiparticles, or let's say all spin 1/2 fermions are massless, essentially leptons and quarks are massless. Or you are in such a condition that you can neglect their mass, then it is true that the helicity commutes with the Dirac Hamiltonian, okay? And therefore, helicity is now a good quantum number for massless particles and antiparticles, and can be used to distinguish between the two degenerate solutions, okay? Which are then simultaneous eigenstates of the Dirac Hamiltonian and of the helicity operator. Let me show this now.
Could you repeat the question, please?
Ripeti, per favore.
Ci fare una domanda, per favore.
Sì, dimmi.
Non ho capito bene perché il momento totale J non può descrivere la degenerazione anche se si conserva.
Perché J è dato dalla somma dello spin più L. ok? E il momento angolare L può assumere qualsiasi valore, quindi J non avrà mai due valori up e down, ma può assumere qualsiasi set di valori, quindi non va bene per descrivere una degenerazione doppia.
Ok, va bene.
Ok, cioè lo spin ha due valori, quindi poteva andare bene, ma se fai spin più momento angolare non va più bene.
Ok, va bene.
Okay, so now let me switch again to Blackboard. Okay, and let's show that indeed the Dirac solutions are eigenstate of the helicity operator. So let's choose a quantization axis. Let's suppose that we work on the z-axis. So we assume that the momentum is non-zero only along z. That means that the momentum vector P is given by 0, 0, and Pz. Okay? Of 0, 0, P. So the full momentum is along the z direction. It has only a z component. Okay, so we work in these conditions, and then let me also write down the scalar product of the Pauli matrix with the momentum operator. Okay, so you can also so scalar product is sigma 1 px plus sigma 2 pz plus sigma 3 py sigma 3 pz, and since px and py are 0, this is nothing less than sigma 3 pz or sigma 3 p. Now let's write down the full expression of the first positive energy particle solution. So U1. U1 in general we found that it is given by square root of P plus M, and then we have 1, 0, Pz over P plus M, and then we have Px plus I Py divided by E plus M. Okay, so this is the solution that we derived last time. Now we force the momentum to be only along Z. Okay, and so this reduces to the root of E plus M 1 0 P, that's the Z or P whatever, divided by P plus M. And now Px and Py are 0, so we get the 0 here. And now we require also that the particle is massless. So M equal to 0, then the solution reduced to square root of E. And then 1, 0, Pz divided by the mass, sorry, by the energy. And 0. Okay? So this is the form of our positive energy, first positive energy particle solution when the momentum is along Z and when we neglect the mass of the particle. Now, let's now apply the helicity operator on this eigenstate here, this vector. And so this is 1 over 2p sigma scalar p 0, 0, sigma scalar p. This is the operator that we find in the slide that I found before. And that is acting on U1. Now, the scalar product reduced to only this piece here, okay? So this is essentially 1 over 2p, and then we have sigma 3p, 0, 0, sigma 3p. or if you like, PZ, okay, the same because it's all in the Z direction. And then this apply again to U1. Now let me continue here. So we can simplify the momentum here. So this is simply 1/2 sigma 3, 0, 0, sigma 3, U1. Let's now put these into a form of 4x4 matrix. So we now substitute the explicit expression of the third power matrices and also the solution of our quadrant. So this is 1/2. Now we have 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, minus 1. And then we have our solution. It's going to be 1, 0, Pz over E, or P over E, whatever. And then 0. And now we make this matrix product. So we have a 4x4 matrix on a 4-component vector. So we have 1 plus 0, 0, 0. So this is going to be 1/2 square root of E. And then we have, so 1 plus 0, 0, 0, 0 is 1. Then we have 0 that multiplies 0 plus 0 plus 0 plus 0 with 0. Then we have 0 plus 0 plus Pz over E plus 0. And then we have 0 plus 0 plus 0 plus 0. But this is nothing else than our spinor. Okay, so we obtain plus 1/2 U1. So our result is, let me write it here, that when we apply the felicity operator over the first positive solution when we neglect the mass, okay, and we move along the Z direction, then this turns out to be plus 1/2 U1. Okay, so this is an eigenvalue equation, okay, for the eigenfunction U1 with eigenvalue plus 1/2. Let's now do the same exercise for the second positive solution, for U2, okay? Again, this is E plus M, then we have 0, 1, Ex minus I Dy divided by E plus M, and minus Ez divided by E plus M. So this is the full expression of the second positive energy solution. Now again, we are moving along the Z axis. So this reduces to square root of P plus M, and then we have 0, 1. This term goes to 0 because Px and Py are 0. And this is minus Pz divided by E. And then we further impose that this works for massless particles, and we got 0, and so this turns out to be square root of E, and then 0, 1, 0, minus, okay, here we still have the mass, sorry, E plus M, now we impose the mass is 0, so this is minus Pz divided by E. Okay. And we do the same job as before. Okay, so we apply our felicity operator now on U2. Okay, it is 1 over 2p, 2p, sigma star t, 0, 0, sigma star t, u2. Okay, we will skip some passages because they are the same. So at the end you obtain 1/2. 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, minus 1, acting on our solution root of E, and then 0, 1, 0, minus pz over E. Okay, now again we make now the product of the matrix with this vector. So we get the 0 plus 0 plus 0 plus 0. So I just continue here. The first element is 0. 0 minus 1, 0, 0. 0, 0, 0, 0. 0, 0, 0 plus z over E. Okay. We can now multiply all these components by minus 1, so we put the minus 1 outside. So it's going to be 1/2 square root of E minus 1, and then 0, 1, 0 minus z over E. That is minus 1/2 square root of E 0, 1, 0 minus z over E, or minus 1/2 u2. And so for the second solution, we obtain this eigenvalue expression. Helicity operator over u2 is equal to minus 1/2 u2. Okay, so u1 is an eigenstate of the helicity operator with eigenvalue plus 1/2. u2 is eigenstate of the helicity operator with eigenvalue minus 1/2. And this is exactly the twofold degeneracy we were looking for. So let's come back to the slide. And this is what we just found on the blackboard. So choosing the direction of motion on the z-axis, of course, this is you can generalize this. Okay, this was just to make a calculation simpler. One obtains for m equals 0 particles these two eigenvalue equations. Okay, so if the mass is equal to 0, spinors u1, u2 are eigenstate of the helicity operator with eigenvalues plus and minus 1/2. What about now the antiparticle solution? Okay, so v1 and v2. So if we repeat exactly the same algebra that I did on the blackboard, but now starting from the expression of v1 and v2, okay, that you find in one of the previous slides, okay, you're gonna get these expressions here, okay, these eigenvalue equations here. But you see they come in the opposite. So the v1 comes with a minus 1/2 and the v2 with a plus 1/2. However, we have to remind ourselves that the physical spin of antiparticle is opposite to that of the particle, as we've shown before, in order to get the commutation between the total angular momentum and the Dirac-Hamiltonian. Okay, so the spin operator for the antiparticle is minus the spin operator for the particle, and as a consequence, by definition, also the helicity of the antiparticle must be opposite to that of the particle. Okay, so in fact here these two are not correct. We have to substitute instead of h minus h for the antiparticle, okay? And when you do so, now we have a minus sign here, a minus sign there, so you obtain this correct eigenvalue equation. So now for v1, we have plus 1/2 eigenvalue, and for v2, we have now the minus 1/2 eigenvalue. So the structure of these two equations for the antiparticle is just the same of the two corresponding particle solution once we take into account that the helicity must be opposite. So let's also visualize this graphically. So U1 and V1, that we can also label as U plus and V plus, represent positive helicity states. That's why we have a plus sign here. And U2, V2, which we can also label as U minus and V minus, represent the negative helicity states. So if this is our Z direction, which is our quantization direction, then for U plus and V plus, you see that the spin and the momentum are parallel, so positive helicity. U minus, V minus, they are anti-parallel, so negative helicity. Okay. Now, let's consider now the ultra-relativistic limit, okay, where the energy is much greater than the mass, so we can, in fact, neglect the mass of our fermions, okay. Then the simultaneous eigenstate of the Dirac-Hamiltonian and the helicity operator, which we will call the helicity spinors, okay, can be written in this explicit form. So this is the explicit form of U plus, U minus, V plus, V minus, in terms of this cosine and sine of theta and this phi angle. So we have two angles here, okay? And the reason why they look in this way is because now we have written the helicity operator in the explicit form by using the spherical polar coordinates for the momentum, okay? So the Pauli-metric stays the same, but the momentum is now expressed, so the x, y, and z component are now expressed in terms of polar coordinates. And once you do this, the helicity operator will look like this. Then you also apply the Euler formula, okay? And then at the end, with some algebra, your helicity spinors will look like this, okay? I think if you're interested in the details of the passages, you find in the textbook, the main textbook, but I will not care about this. So once more, U plus, U minus, V plus, V minus are both simultaneously solutions of the Dirac equation for the free fermion and also eigenstate of the helicity operator. Now, let's consider what happens now if we cannot neglect the mass of particles, okay? Now, you know already that since a massive particle moves in the vacuum at a speed which is lower than the speed of light in the vacuum, okay, then it is always possible to find a reference frame that moves faster than your particle, okay? And from such reference frame, the momentum of the particle appears in the opposite direction, appears reversed, while the spin, of course, is unchanged, okay? So the helicity is opposite in the two frames. So suppose you are positive helicity in your frame, then you find another frame which moves faster than your frame, okay, because you are massive, so you are moving slower than the speed of light. Then in this new frame, the helicity will be opposite. And so it turns out that for massive particle in general, the helicity is not a Lorentz invariant. It depends on the choice of your reference frame. So the fact that the eigenstate of the Dirac-Hamiltonian are also eigenstate of the helicity operator, and thus that helicity is a good quantum number, is only approximately true for massive particle, okay, when the mass is not equal to 0. And more precisely, it is true at the level of V over C, okay? So for instance, if you have, so this approximation is very good if you have light, ultra-relativistic light particles, okay, which move very close to the speed of light. Then this ratio goes to 1, and essentially, the helicity quantum number is conserved. However, if you have, as a result of a reaction or a decay, heavier particles, okay, which move slower, okay, then this is not true, and the approximation you have is given by the ratio V over C, and this you can also visualize in this table here. Okay, so these are the four helicity spinors. U plus, U minus for particle, V plus, V minus for antiparticle. Then, if your particle is perfectly massless or you completely neglect your mass, then the eigenvalue, as we have seen in the blackboard, are plus or minus 1/2. However, if you cannot neglect the mass, okay, and so if your speed is lower than the speed of light, then you have to correct this 1/2 by the ratio V over C, okay? And this is your, let's say, level of approximation. So let me now summarize in this slide what we have learned. So the Dirac theory guarantees both linear and total angular momentum conservation, since both the momentum and the total angular momentum operator commute with the Dirac Hamiltonian. Then, spin arises naturally in the Dirac theory. It does not need to be introduced ad hoc as in non-relativistic quantum mechanics, essentially spin 1/2, okay? Spin orbit interaction energy, such as terms proportional to the scalar product of L and S, naturally arising from the Dirac theory, nicely explain the observed tiny splitting in some atomic excited level, which is the lump shift. This we will study in the next week, okay? And thus providing a relativistic correction to the atomic energy levels and leading to the correct value of the fine structure constant, okay? This is a very relevant point. We will study next week, I think. And this is essentially one of the best proof of the Dirac theory, okay? The best triumphs. Not only this. Now, we also introduce the magnetic moment for an, let's say, Dirac particle or an electron. So in general, it is defined by this, but then the Dirac theory predicts that the value of the zero magnetic ratio is exactly 2, and this is precisely verified experimentally, okay? And this experimental verification that G is equal to 2 to very, very, very high precision, of course, was another major triumph of the Dirac theory, okay? Together with the existence of antiparticles, of course, as we've seen last time, and together with the lump shift, okay? Now, helicity turns out to be a good quantum number for massless particles and massless antiparticles, and can be used to distinguish between the two degenerate solutions. And so now we can interpret our set of 4 solutions completely. So the 4 solutions are interpreted as 2 particle solutions and 2 antiparticle solutions, and the twofold degeneracy represents the 2 helicity states, either positive or negative. And this explains why we, in the previous lesson, we also use the notation phi plus, phi minus, k plus, and k minus for the 2 component spin, okay? So these phi plus and k plus corresponds to the positive helicity, and phi minus, k minus to the negative helicity, okay? So we now completely understood why Dirac equation provides 4 different solutions, and we also made a physical interpretation of this. Now, there is another quantity which is related to chirality, and it is called, to helicity, and it is called chirality. Now, chiral states are eigenstate of the operator gamma 5, which is defined in terms of the Dirac gamma matrices in this way. So gamma 5 is I, gamma 0, gamma 1, gamma 2, gamma 3. If you make this matrix product, you obtain this expression for gamma 5 that you can also write in terms of the 2 by 2 identity matrix. And it turns out that the square of gamma 5 is the identity matrix, 4 by 4 identity matrix. And also, one has to take into account this anti-commutation rule. Okay, so gamma 5 gamma mu is equal to minus gamma mu gamma 5. Now, now once we have introduced chirality, we can construct the following combinations of solutions, okay, which are simultaneous eigenstate of the Dirac Hamiltonian and the chirality operator. So we call the right-handed, so R stands for right-handed. The right-handed chiral eigenstate, it is obtained from the standard spinor by multiplying 1/2 1 plus gamma 5. And this object here we can also call the left projector, so which is an operator that projects our spinor into a right-handed spinor. Sorry. And the same for the left-handed. Okay, so we can define a left-handed spinor, okay, as the standard spinor multiplied by this operator, 1/2 1 minus gamma 5. Okay, which are in fact the so-called chirality operator. Okay, or gamma 5 essentially is the chiral operator. So once you define the right-handed and the left-handed eigenstates, okay, you can also, they of course have to satisfy this trivial eigenvalue equation. So gamma 5 psi r is equal to plus 1 psi r, gamma 5 to psi l is equal to minus 1 psi l. Okay, so these are the eigenvalue equations for these right-handed and left-handed chiral spinors. And then, of course, we can do the same for the adjoint spinor. Okay, so we can have the adjoint right-handed spinor And now this is obtained in the opposite by using, if you want to have the right-handed adjoint spinor, you have to use the left projector. If you want to have the left-handed, you have to use the right projector. Okay. And also, of course, here we have the corresponding eigenvalue equation for the adjoint right-handed and left-handed spinors. Okay. In this case, the right-handed corresponds to -1 eigenvalue and the left-handed to +1 eigenvalue. Now, while the spin and helicity are properties of the two component spinors, phi and k, and can be directly measured, so experimentally measured, chirality is a property of the full solution, so it's a property of the four-component spinor, and it cannot be measured experimentally. Okay. However, helicity and chirality are strictly linked to each other in the limit where you can neglect the mass. Okay. Essentially, for massless particle, the chirality operator coincides with the helicity operator. Okay. Or if you like, when we can neglect the mass, the helicity operator corresponds to the chirality operator, and therefore helicity is a good quantum number. And also, one can interchange now the helicity operator with the chiral operator in the massless limit. Okay, so it turns out that the positive helicity operator corresponds to the right-handed. Sorry, the positive helicity eigenstate corresponds to the right-handed eigenstate or spinor, which is defined this way. The negative helicity spinor corresponds to the left-handed spinor, which is defined in terms of the left-handed operator, and then we have the opposite relation, okay, for the adjoint spinors, and these are the standard eigenvalue equation for the chiral operator, Okay, so only in the limit where the mass is 0 or can be set to 0, then the helicity eigenstates corresponds to the chiral eigenstates. So in general, this is the rule. For massless particle, the left chirality corresponds to negative helicity, and you see here, and the right chirality corresponds to the positive helicity, and you see there. This is completely true for massless particle, but only approximately true for massive ultra-relativistic particle, okay? And it is, of course, completely wrong for massive non-relativistic particles, for non-relativistic particles in general, okay? Because then the approximation becomes really, really wrong. Now, in practice, if you have a massive particle, okay, it is an admixture, a mixing of the correct helicity state, which is the dominant term, and the wrong helicity state, okay, which is, let's say, a contamination, okay, and which is suppressed by m over e. So the more you can neglect the mass, of course, with respect to energy, then the wrong component becomes negligible, and everything is dominated by the correct helicity. Okay. Now, something that you can immediately verify is that any spinor, U or V, can always be decomposed into a left-handed and a right-handed chiral component. Okay, so you can always decompose as U left-handed plus U right-handed. And so if you now apply here the right-handed and the left-handed projection operator, okay, you obtain this expression. And then if you just make the sum here, you immediately obtain U. You get 1/2 plus 1/2, and then you get which makes 1, and then these cancel with this. Okay, so this is trivial. Let's now make use of this relation to see how helicity conservation affects the vector current that we defined last time. So let me switch again to the blackboard. Right. So last time we found that we can define a vector current J as a joint vector gamma mu and the adjoint spinor gamma mu and the spinor. Okay. And now we just learned that we can always decompose the spinor and the adjoint spinor in terms of the left-handed and right-handed spinor. So this is a UL plus U right gamma mu And then you have U, L, U, R, U. So let's now take all the products here. So we're going to have UL adjoint, gamma mu UL, plus UL adjoint, gamma mu UR, plus UR adjoint, gamma mu UL, plus UR adjoint, gamma mu UR. So we have 4 terms. Let's call these so LL, LR, RL, RR. Okay, so let's try to calculate now, for instance, this one. So the current JLR. So this is given by UL, gamma mu UR. Now we make use of the kernel projection operators. So this is U, 1/2, 1 plus gamma 5. Then we have gamma mu, and then we have 1/2, 1 plus gamma 5, U. Let me remind you that if you have a right spinor, you have to use the right projection operator, but if you have, let's say, a left adjoint spinor, you have to use the opposite. So the right projection operator to get a left-handed adjoint spinor. Okay, so now we make some simple passages. So we multiply gamma mu here. So this is 1/4. Then we have U bar. Then we have gamma mu plus gamma 5 gamma mu. And then we have 1 plus gamma 5 U. Now we apply here the anti-commutation relation between gamma 5 and gamma mu. Okay? So this is 1/4 U bar gamma mu minus, we swap the two, gamma mu gamma 5, 1 plus gamma 5 U. Now we put gamma mu outside, so this is 1/4 U bar gamma mu, and then we have 1 minus gamma 5, 1 plus gamma 5 U. It is 1/4 adjoint spinor gamma mu. Now this is just 1 minus gamma 5 squared, and then we have U. But gamma 5 squared is just 1, is the identity matrix. So this goes to 0 and everything is 0. So what you obtain is that this current here, okay, where we have mixed chirality, is 0. And you can, of course, repeat the exercise for the other mixed term. RL is also going to be 0, just do the same thing here. Okay? Whereas it turns out that JLL and JRR, so with the pure terms, are not 0. So essentially, if we write down our overcurrent J, U bar gamma mu U, okay, we will only survive with these two terms here. So this will be just UL gamma mu UL plus UR gamma mu UR. Okay. And if you do the same exercise for the antiparticle spinors, you will find J is equal to V bar gamma mu V Okay, also here only the pure terms will survive. VL, gamma mu, VL plus VR, gamma mu, VR. So let's try to interpret this result. I come back to the slide. So what we found is that particle-particle or antiparticle-antiparticle vector currents with mixed chirality states cannot exist. They are exactly zero. Okay. And as a consequence, in ultra-relativistic regime, okay, where you can neglect the mass, helicity is conserved for any interaction that concern vector currents. So currents given like U bar, gamma mu, U. Okay. And this is exactly the case for instance, the electromagnetic interaction, as we study next week. So this is exactly the case for the quantum electrodynamics and also of QCD, by the quantum chromodynamics. This is not the case for the weak interaction, as we study. Okay. So once more, a consequence of this is that the helicity is conserved in any interaction that concerns vector currents. And so that means that the helicity of a particle leaving, let's say, QED vertex is the same as that entering. So let's consider now these four, let's say, piece of Feynman diagram. We will understand all these, of course, next lessons. So here we have essentially, let's say, an electron, an incoming electron that emits a photon. Okay, and here where the arrows put, let's say, backward in time, this is an old notation, but this is still used. This is the antiparticle. So if this is an electron, this is a positron. Okay, so this is a positron emitting a photon, essentially. Now, the black arrow is the spin, the blue arrow is the momentum. So you see that the helicity is positive here and positive there. Okay, so the helicity of the particle that entered the vertex is the same as the particle that exiting the vertex. This is negative helicity. Okay, spin and momentum are opposite, and this is also negative helicity. So again, helicity is conserved at this vertex. And this is the same for antifermions. Okay, so suppose for positrons. Okay, positive helicity entering, positive helicity exit. A negative helicity entering, negative helicity exit. Ok? Allora, facciamo una pausa? Avete domande?
No, tutto bene.
Ok. Allora direi facciamo una pausa breve perché poi ho un po' da fare. Devo un po', fatemi un attimo vedere quanto mi resta qui. Vabbè, dai, facciamo alle 10:15, va bene?
D'accordo.
10:15 ripetiamo.
Salve.
Ok, riprendiamo? Ci siete?
Sì, sì.
Okay.
Sì.
Va bene. Allora, Adesso diciamo, andiamo sulla seconda, no, la terza parte, diciamo, completiamo il modulo 2, in realtà non oggi ma domani, sì, domani. E questa diciamo, è l'ultima parte di questa introduzione teorica formale, che però ci servirà tantissimo poi appunto per quando andremo poi a toccare con mano la fisica, ok? Quindi adesso cominciamo questo capitolo che è dedicato alle quantum field theory e alle simmetrie e leggi di conservazione. Ok. So the quantum field theory has emerged as the most successful theoretical framework for constructing quantum mechanical theories of elementary particles, and in fact it constitutes the theoretical framework, the theoretical basis of the standard model of particles and interaction as we studied. Okay? Now, what is in general a classical field? A classical field, as you know, is a function of coordinates and time, which is defined over some region in space and time, in fact. And we have two major examples here, the Newtonian gravitational field, okay, G, RT, or the electromagnetic or electric and magnetic field, if you want. Okay, they are all classical fields. Now, first, classical field theory do not account for the quantum mechanical behavior of subatomic particles. So what we need is a quantum field theory, okay? Not a classical field theory, but a quantum field theory. And now, a quantum field is something completely different. Okay, quantum field is an entity with infinite degrees of freedom, which is described in every point of space-time, x mu, by an operator. Okay, so the classical field are functions of space and time separately. A quantum field is an operator, okay, which depends on the space-time coordinate x mu, and which corresponds to infinite degrees of freedom. Now, in quantum field theory, each elementary particle, either leptons, quarks, bosons, is associated to a quantum field. So more precisely, elementary particles are generated as excitations of the corresponding field, or as quanta of the corresponding field. For instance, the electron, the particle, arises as an excitation of the electron field, the Higgs boson arises as an excitation of the Higgs field, and so on. So this applies to all elementary particles. And this is nothing else than a generalization of the more common concept that photons are the quanta of the electromagnetic field. Okay? Now, for historical reasons, the procedure through which the fields are quantized is known as second quantization, whereas we refer to the first quantization to indicate the ordinary quantum mechanics. Now, a description of the second quantization goes beyond this course. Okay, this we'll find in a course of quantum field theory, like the one by Moretti. Okay, so what I will give you in the next slides is just some basic ideas. Okay, so try to follow the main ideas and don't waste yourself into the details. Okay, it's just to give an idea as quantum field theory work, and then we'll move on. So let's do this through a comparison between quantum mechanics and quantum field theory. Okay. So in quantum mechanics, as you know, the wave function is defined for a fixed number of particles. For instance, you can have a single particle wave function, and it is subject to the action of an operator describing a certain physical observable. So the position operator, momentum operator, angular momentum operator, spin operator, and so on. Okay. So it is an operator describing a physical observable that acts on your wave function. Sorry. In quantum field theory, since the field itself is an operator, okay, so the things works in opposite direction. It is the operator itself, so the field itself, that acts on the space of states by creating and destroying a particle through specific creation and annihilation operators. And then the wave function, in the case of quantum field theory, describes a multi-particle state, but not with fixed number. So the number of this multi-particle state can vary over time, because particles can be created and destroyed, annihilated, through these creation and annihilation operators. So it's conceptually very different, okay? Now, of course, here we have much more flexibility, okay? Because we are not stuck to fixed number of particles, states, but the number of particles in each state can vary over time. And of course, this flexibility allows, for instance, to study particle process like this one. Okay, so the electron-positron annihilation to gamma, which in the language of quantum field theory is interpreted as an electron and a positron which annihilate, so they are destroyed by the destruction, the annihilation operator, and then two photons are created by the creation operator. Okay. What about now the Klein-Gordon and the Dirac equation that we derived last time? So they both remain valid in quantum field theory, but now their solution have now a completely different meaning. They now represent a multi-particle excitation of a quantized field. We will see some examples. Now, again, let's make a comparison between the wave function in quantum mechanics and in quantum field theory. Okay, so in quantum mechanics, the wave function of a multi-particle state must be symmetric for exchange of identical bosons, as you know, and antisymmetric for exchange of identical fermions. Okay. Now, let's take an example. So let's consider the wave function for a system of n identical bosons. Okay. So this is the standard quantum mechanical description, where phi k or phi I is the wave function of each boson, okay, that take part of this multi-boson state. So this is a single particle wave function, each of those here, okay. And the sum here runs over all possible permutation of decay elements, okay. So to make a concrete example, suppose we have a system of three identical bosons, one of which is in the state phi1 and the other two are in the state phi2. Okay, then the wave function would look like this way. So we have 1 over square root of 3 factorial, and then we have the three permutations of these three bosons into the two possible states, phi1 and phi2. Okay. Now this is a very simple state with only three bosons, and you see already how complicated is the quantum mechanical wave function. And then you can imagine if you have to deal with, let's say, a boson condensate with thousands of millions of bosons. So, of course, this is impossible to handle this kind of notation. In quantum field theory, instead, one has just simple to list the number of particles in each quantum state. And so this complicated wave function in a quantum field theory would simply look like 1, 2, 0, 0. That means one boson in the first state, two boson in the second state, phi2, 0 boson in the third, 0 boson in the fourth, and so on. So you see how the notation is, of course, much more easy to handle. And let's now see how we can construct this wave function in quantum field theory. So, in quantum field theory, any multi-particle state, such as this one, for example, is obtained as the result of creating and destroying particles through, as I was saying before, specific creation and annihilation operators. Okay. Now, the creation and annihilation operators, which are denoted in this way, so A delta for the creation and A for the annihilation, they arise, okay, through the Fourier decomposition of the quantum field in terms of a plane wave. Okay. So now, don't waste your time trying to understand fully what is written here. Let me just say that you can always decompose your field, okay, essentially into a creation, annihilation and creation operator through this Fourier decomposition. Okay. Now, how do we define the vacuum state in a quantum field theory? The vacuum state, which we call zero, okay, is defined through the action of the initiator operator. So the vacuum state is that state that remains the same when we apply the annihilation operator. So if you want to annihilate the vacuum, you always get the vacuum itself. The one particle state, as a consequence, is obtained by applying the creation operator to the vacuum state. So you start from your vacuum state, you apply the creation operator, and you create now one particle. Okay? And in general, of course, one can use the creation and the annihilation operators recursively to generate quantum states with the desired number of particles. So suppose you start with an n particle state, you apply the annihilation operator, you end up with an n minus 1 particle state. Or suppose you create a new particle, so you move from n particle state to an n plus 1 particle state. Okay, so this is essentially quite trivial to play around with the number of particles in quantum state in quantum field theory. Let's make something more realistic. Okay, so let's try to construct an n particle state by simply applying the creation operator to the vacuum state. Okay, so consider, for instance, n identical particles with momentum p, so the same momentum of all particles, and this we can construct simply by applying n times the creation operator to the vacuum state. Okay, if you do this n times, you would obtain an n particle state here. Okay, and this you can, of course, also write in a more compact way as the power to n of the creation operator divided by the square root of n factorial. Now, this is, of course, a very trivial case where all particles have the same momentum, so they all come in the same quantum state. Then, of course, one can generalize this to the case of n particle in, let's say, m different quantum states, or with m different momenta, for instance. Okay, so this is the notation, n1, p1, so yeah, n1, p1, and 2, and so on. So this is the number of particles with momentum p1, number of particles with momentum p2, and the number of particles with momentum pm. And then you generalize your notation here. So you now apply n times for each momentum the creation operator to the vacuum, and you multiply by the number of quantum states you want to create. Okay, and so at the end, what you obtain is the generalization of what I was showing before. Okay, so this is the way multi-particle states are created, created in quantum field theory, are constructed in quantum field theory. Now, the dynamics of quantum field in quantum field theory is described by the Lagrangian density. Okay, so let's see now what the Lagrangian density is, but let me first remind you the classical Lagrangian formalism that you know very well. So for a given physical system, let's say a classical system, the Lagrangian is defined as the kinetic energy minus the potential energy in general. Okay. And then, as you know already, given the Lagrangian of a system, in classical mechanics, you can derive the equation of motion just by substituting your Lagrangian into the Euler-Lagrangian equation and solving this equation. Okay, where Q are generalized coordinates. Okay, so spatial coordinates and momentum coordinates, and Q point is just the time derivative. Okay, so you know this very well from classical mechanics. Now, there is, however, a problem here if you want to be Lorentz invariant, because the Euler-Lagrangian equation are derived by imposing, so all these actually is derived by imposing the stationarity of an action, which is defined as the time integral of the Lagrangian. Okay, but then as you see here, the time has a special role, and this is not, of course, a Lorentz invariant argument. Okay, in a covariant formulation, you want to have the spatial coordinates and the time components to be treated in the same way. So we cannot, of course, use the classical formalism in quantum field theory. We need to introduce the concept of Lagrangian density. Okay, so the Lagrangian density is such that the classical Lagrangian is given by the volume integral over the Lagrangian density. Okay, and once you do so, then you can define properly your action, because the action is still the Lagrangian in time, but now you have both the spatial coordinates and time. So your action in quantum field theory is the integral of the Lagrangian density, okay, in the 4-space volume. So considering not only the spatial coordinates, but also the time, and this at the same level. So this is now a Lorentz invariant action, and so you can derive now a Lorentz invariant theory for this, okay? In particular, what we do essentially is that we replace the standard, the classical Lagrangian, L, Q dot T, into these Lagrangian now expressed in terms of quantum fields. So instead of the generalized coordinate, you have your field. Instead of the time derivative of the coordinate, you have now the derivative of your field that is your space-time coordinate. And instead of just time, you have now all 4 space-time coordinates. Okay? So now this object is now completely Lorentz invariant and can be treated, okay, of course, in a quantum field theory, in a relativistic quantum field theory. And then, of course, we can substitute this Lagrangian density into the Lorentz invariant Euler-Lagrangian equation, okay, which is essentially the same as the classical one, but now you have here the fields, okay, instead of the coordinates, and you have the derivative over the position for vector, okay. And this you can also write in a more compact form, you know, that in the x mu, you can just write as the mu, and also here, inside here. Okay, so these are now the Lorentz invariant Euler-Lagrangian equation. So if you can describe your system with your quantum field system with a given Lagrangian density, you substitute here, you solve these, and you obtain the dynamics, so the equation of motion for your system. Okay, and we will now try to do so. Okay, so let's now start for the case of a scalar field. Scalar means spin equals 0. Okay, and so the Lagrangian density, let's say the most simple Lagrangian density for a scalar field is given in this way. Is 1/2 the mu phi, and then we have this mass term. Okay, so the first term is the kinetic energy essentially, and the second term is just the mass term. We suppose for the moment we are treating a free particle, so there is no potential, no interaction potential. So you just have the kinetic energy and the mass energy. Okay, let me just note you that the mass energy comes with a quadratic term in the field. Okay, this will be, as we will see, very relevant when we study the Higgs mechanism at the end of the course. Okay, because the Higgs particle is a scalar particle, the scalar field. Okay, so this is, let's say, the most simple way you can write down invariant Lagrangian density for a free scalar particle. But we know already that the dynamics of a free scalar particle is described by the Klein-Gordon equation. Okay, so what we expect is that if we now insert this Lagrangian density into the Lorentz invariant Euler-Lagrangian equation, we should obtain back the Klein-Gordon equation. And let's now try to show this. So the Lagrangian for a scalar is 1/2 the mu phi, which are clearly second order derivatives of all, minus 1/2 mass squared pi squared. Okay, and then we have our Euler-Lagrangian equation, which is the mu derivative of the Lagrangian density with respect to the derivative of the field minus derivative of the Lagrangian density with respect to the field itself, and this is equal to 0. So let's calculate now separately the two pieces of this equation, and then we put everything together. Okay, so let's start with the second piece, which is the easiest. So dl in the field, okay, is the derivative with respect to the field of this expression. So the field only enters in the last term here, because here it enters through a derivative. Okay. So the only piece that concerns the last part of the Euler-Lagrangian equation is the second piece. So this we just take the derivative of this, which is 1/2 m squared to pi. And so this is, and then we have also minus sign, minus m squared pi. Now we attack this part here, okay, the one into the big parentheses. So we have dl in the mu phi. Okay, that is the in the mu phi of our Lagrangian density, so it's 1/2 the mu phi minus 1/2 m squared pi squared. Now, the derivative of the field only enters in this piece here, it does not enter here, so this goes to 0 in the derivative, and this is essentially a second order derivative, so this is something like the mu phi to the second if you want. So when you take now the derivative of this, we have 1/2 here, so we have a square here, this is just the mu phi. Okay, and now we simply put everything together, okay, into our Euler-Lagrangian equation. So we're going to have the mu, the mu. Then we have what we obtain here, that is the mu p minus, and then we have this minus m squared pi, so this becomes a plus m squared pi equal to 0. So this is how our Euler-Lagrangian equation reduces. And this you can even write in a more compact way, okay? You can now put together this, so this is going to be the mu plus m squared pi equal to 0, which is, in fact, the Klein-Gordon equation in the covariant form, as we derived last time. Okay? So this proves, in fact, that this is the Lagrangian density for a free scalar field. Let's come back here. Okay, so this was for a scalar particle. Let's now see what happened for a spin-1/2 particle. So the most simple Lagrangian density for a spin-1/2 particle, so for a Dirac particle, is written here. So is I is the adjoint spinor, the mu derivate, and then we have this bilinear term for the mass. Okay. So the first term again is the kinetic energy, and the second term, which is bilinear into the field psi, is the mass of the fermionic field psi. Okay. There is no interaction potential because we are working in the simple case of free particles, so not interacting particles. And so again, we expect that if we now put the Lagrangian density into the Euler-Lagrangian equation, we would obtain, of course, the Dirac equation. And let's show this. Okay. For the case of the spin-1/2 fermion, one has to consider the field and the adjoint as two different. So the spinor and the adjoint spinor as two independent fields. Okay. So we start from our Lagrangian, okay, which is I, C bar, gamma mu, the mu, psi minus m C bar psi, okay? And let's first consider the Euler-Lagrangian equation for the case. So we first consider the case where our field is the adjoint solution. Okay? So the Euler-Lagrangian equation becomes the mu, the L in the mu adjoint minus the L in the adjoint equal to 0. Now, as before, let's calculate piece by piece, okay, the terms of this equation. The first piece, okay, the one in parentheses, the L in the mu C bar is trivially 0, okay, because in our Lagrangian density we don't have any term that goes with the derivative of the adjoint spinor. The only derivative acts on the spinor, not on the adjoint spinor. So this term is trivially 0. So let's now concentrate on the other term. dl over d psi. It is that in the psi. And here we put our Lagrangian, so it's I, psi bar, gamma mu, the mu psi, minus m psi bar psi. So we have to take the derivative of this with respect to psi bar. And now we have two contributions because psi bar enters here and also here. And so when we take this derivative, we're going to have I, gamma mu, the mu psi from the first term, and minus m psi for the second term. So now we substitute into our equation. So this term is 0. We only have this one with opposite sign. So we can have minus no, sorry, 0 minus and then minus I gamma mu the mu C minus and C, and this has to be equal to 0. So this is our now Euler equation, which we can write as E gamma mu, the mu minus m psi equal to 0, and so this is clearly the Dirac equation. Okay?
Ok.
Now, let's take the other option. So we now take the field phi just for the standard spinor, and we do the same exercise. So let's first calculate the first term of the Euler-Lagrange equation, the L in the mu psi, now it's the standard spinor. It is the mu psi of our density. So I C bar gamma mu the mu psi minus m psi bar psi. Now the derivative with respect to the derivative of C, which is this term here, okay, only affect the first part, and it is 0 on the other side because we don't have any derivative here. So this is just I C bar and gamma mu. Let's now take the second piece of the Euler-Lagrange equation, so the L over D psi. So it's D on this side of I psi bar gamma mu the mu psi minus m psi bar psi. And here we only have a contribution from this term here, because here you can together the derivative. Okay, so the derivative with respect to psi is only this term here. So this is just minus m psi bar. So let me put everything together into the Euler-Lagrange equation. So the mu dl over d the mu psi minus dl over d psi equal to 0. Let's substitute all our pieces. And so we're going to have the mu. This first part is just I psi bar gamma mu. And then we have minus, we have a minus, so plus, and psi bar equal to 0. So the proper way to write this, since we have here an unknown spinor, is that the derivative should act to the left. So this is more correctly written as I psi, and then the derivative acting from the left, from the right to the left, okay? Gamma mu plus m psi bar equal to 0. And so finally this is nothing else than psi bar I the mu gamma mu plus m equal to 0. That is, as you already see, the adjoint Dirac equation. Okay. So for the training of the equation was easier because we just have the field. Here we have the field and the spinor and the joint spinor. So we have to work out these twice, okay, with the two hypotheses, and we get in one case the Dirac equation, in the other case, obviously the algebraic Dirac equation. Okay. So let me come back to the slide. Okay. So we proved that this is the, let's say, a Lagrangian for a free scalar particle, and this is a Lagrangian for a free spin-1/2 Dirac particle. Okay. We will make a lot of use of these two Lagrangian densities in the future. Now, so far we have considered the simple case of free fields, so not interacting fields. Of course, in general, fields can interact with each other or with a potential, and so we should also consider an interaction term in the Lagrangian density. So we have the unperturbated or free Lagrangian term plus some interaction term. No? Now, as we have already anticipated a few lessons ago, one can obtain reliable predictions on amplitude of physical processes, such as scattering, reactions, or decay, through the perturbation theory by just assuming that this interaction term is just a small perturbation. Okay, and then you make a power expansion in this essentially in this small value here, or to be more correct, okay. So this interaction Lagrangian density will be proportional to a small parameter lambda, let's say. Then you make a power expansion into lambda, okay? You see that only the first few orders are relevant, and then you, as soon as you go to higher order, their contribution becomes negligible and negligible. And so you already obtain a very reliable prediction if you stop your expansion at the first few orders, okay? This is a very powerful technique, of course, to get prediction for cross-sections and decay rates. One golden example of this is quantum electrodynamics that we will start studying by tomorrow. Okay, that, as we will see, is the quantum field theory of the electromagnetic interaction. Okay, and in case of quantum of QED, the small parameter is in fact the fine structure constant. Okay, which is 1/137. So you see, this is a small number, so you can easily make a power expansion over this small parameter. Okay, and when you take order up to the second power or third power, they become more and more negligible. Okay. Now it turns out that QED, based on the perturbation approach, okay, by using this fine structure constant as the, let's say, the smallness parameter, it has an extraordinary predictive power. The prediction of QED are proved to be correct when you compare to experiment to within 1 part over 10 to the 8. In fact, QED is considered to be one of the most successful physical theory ever developed. Okay, so it's a huge success. Okay, and the agreement with experimental data is incredibly high. This is unfortunately not the case for QCD. QCD, as you know, is the theory of strong interaction, the quantum chromodynamics. Okay, and the reason is that differently from QED, the parameter, the coupling of the QCD is not small, okay? It's not such a small number. It can be as large as 1, for instance. And so you cannot perform a power expansion in this parameter because the theory will explode completely, okay? To be more precise, as we study, there are two regimes of QCD, okay? The regime of asymptotic freedom where this quantity, where the strong constant becomes small and you can still use perturbation methods. And then we have the non-perturbative regime, the opposite, where the coupling constant becomes large, so you cannot use a perturbative approach. And then in this regime, QCD is not predictive at all. Okay, the only way to learn about strong interaction in this non-perturbative regime is to make experiments and look at experimental data. You will not get prediction from first principles from the theory, unless you make, of course, assumptions, and so you use models, as we will see, okay, but not from first principles. So in general, these interaction term in the Lagrangian density, we can decompose into the three main contributions from the three main interactions, which are electromagnetic, weak interaction, and strong interaction. Of course, we are completely neglecting here the gravitational interaction, which is completely negligible at the scale of subnuclear scale. Okay. And of course, the specific form of these various terms depends on the properties of these interactions. So more general on the symmetries of these three interactions above. So let's now speak for the next 10 minutes about symmetries and conservation rules. So you probably know already about the Nether theorem. This can be applied to essentially to any field of physics. Okay. So the Nether theorem tells that if the Lagrangian of a physics system is invariant or symmetric, which is the same, under a certain group of transformations, then there must be a set of physical quantities that is conserved, and vice versa. So it is an extremely powerful theorem. Let's consider now some case of transformation. So let's consider the so-called space-type transformation. This includes the translations, rotations, time displacement, and also Lorentz transformations. So altogether, they form a group of transformations which is called the Poincare group. And this is extremely relevant because the invariance of the Lagrangian of any physical system with respect to the Poincare group of transformation results in the conservation of momentum, energy, and angular momentum, okay, which is at the basis. Now, a few words still on the transformation, and then we will see more tomorrow, okay? So we can categorize the transformation according to their features, okay? So first of all, let me divide transformation into two main categories. The first category is the discrete transformation. And examples that we will study are parity, charge conjugation, and so on. In this case, the parameters of the transformation can only take discrete values, not continuous, but only discrete values. And another important feature is that the corresponding conservation laws are multiplicative. That means that only the product of the relevant quantum numbers is a conserved quantity. Then we have the continuous transformation, the other group, okay? And this includes, for instance, a spatial transformation, rotation, and many more. And now, in this case, a finite continuous transformation can be obtained through an infinite sequence of infinitesimal transformations. Okay? So this you can only do with continuous transformation, but cannot apply to discrete transformation. So any finite transformation you can obtain has an infinite sequence of infinitesimal transformations. And in this case, the corresponding conservation laws are additive. That means that not the product, but the sum of the relevant quantum numbers is a conserved quantity in this case. But then we can also split even further our transformation, okay? So the continuous transformation are divided into space-time transformation, which include the parity, translation, rotation, and so on, and internal transformation. That means transformation that act on internal quantum numbers, such as isospin, strangeness, and so on. We will study this, of course, next in the course, okay? But then, internal transformation can further divide into global transformation and local transformation, or gauge transformation. So the global transformation means that the parameters of the transformation do not depend on the space-time coordinate x mu. An example that we will study are SU2 isospin, SU3 flavor, etc. Instead, the local transformation or gauge transformation, which are those relevant for the standard model, essentially, okay, are transformations in which the parameters depend now on the space-time coordinate. So they are different. These parameters are not global, but they are different in different points of the space-time. An example are the gauge transformation of the QAD, which is U1 electromagnetic, the gauge transformation of the weak interaction, SU2L, the gauge transformation of QCD, SU2 color, etc. And so now this diagram essentially repeats what I've said already by words. So the transformation divided into two main categories: discrete transformation, such as parity, charge conjugation, etc., and continuous transformation. The continuous transformation can be further divided into space-time transformation, such as translation, rotation, Lorentz transformation, and internal transformation that act on internal quantum numbers. And those can be further divided into global transformation, where the parameter of the transformation do not depend on the space-time coordinate, or local transformation, also said gauge transformation, where instead the parameter depends on the specific position in space-time, specific coordinate. Ok, questa è l'ultima slide di oggi, domani riprendiamo esattamente da questo punto. Ci sono domande?
No, per me... Ok.
Ok.
No,
Va bene, allora adesso stacco la registrazione, vediamo come è venuta oggi, vediamo se aver risolto, eventualmente useremo quella del nostro collega. Ci vediamo domani alle 11. Domani completeremo questa parte qua, quindi parlando adesso delle trasformazioni, applicandole alla lagrangiana, quindi sia funzioni locali che globali, e poi alla fine cominceremo a parlare finalmente della QED, okay? La teoria di campo delle interazioni elettromagnetiche. Va bene, ci vediamo domani.
Arrivederci.
Arrivederci.
Domani.
arrivederci.
Buona giornata.